Okay, in our final lecture, we are going to take a look at regulating the glomerular filtration rate, or GFR. I'm going to start by posing a hypothetical question. Why? Why is it important to regulate the GFR? What happens if we don't? What happens if the GFR gets too high? What happens if the GFR gets too low? I don't expect you to have a really strong mastery of this at this stage, especially because it really requires some understanding of what happens further along in the nephron, but I'm going to try to walk you through it so that you can understand, at the very least, that it is important that the GFR not get too high or too low. So remember, the GFR, or the glomerular filtration rate, is a measurement of how much fluid is becoming filtrate per day across all of the kidneys, right? And we've set a benchmark of about 180 liters. Well, that filtrate is moving through the nephron, and what the nephron is doing is basically picking stuff out. In other words, it's saying, I want that, I want that, I want that. So you can imagine a cell in the nephron watching stuff move by and be like, yoink, 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 I want that, I want that. And it turns out that a certain flow rate of the fluid is required to optimize your ability to pick stuff out. And that has to do with transport rate of different transporters. So I'm just going to give you an example here. And again, it's just something to kind of try to grasp a little bit so you can understand or try to predict what the consequences would be if the GFR was much too high or much too low. Imagine that I'm a glucose transporter. Okay, so I'm a glucose transporter, and I'm watching the filtrate go by, and I'm going to grab glucose every time I see it. As a glucose transporter, I'm a carrier protein, which means that I'm subject to saturation. And I also work at a specific rate. So if the filtrate was moving by reasonably fast, I might be pick, and get it all. But what if it starts shooting through really fast? If it moves through too quickly, then I may not be able to pick out all the glucose because as I'm grabbing one, another one shoots by. And I didn't have enough time to grab it. So if the glomerular filtration rate is too high, then the filtrate is going to move too quickly through the tubule. And if the filtrate moves through too quickly through that tubule, you will not have a chance to reabsorb everything you want. The outcome is going to be that you are going to end up with urine that has a bunch of stuff that you actually wanted to put back in your body, including ions. And if you don't grab back all those ions, it can lead to an ion imbalance, which can lead to a lot of other problems like heart palpitations. So we don't want that. That would be bad. In the same line of thinking, if the GFR is too low, then barely any fluid is getting out, and then the fluid is just creeping along. And it turns out that a lot of our transporters are in fact designed for fluid to move at a very particular speed. And so when they just creep along way too slowly, you have too much time with it. You're all, whoop, 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 I grabbed it all. And then you're like, no, you weren't supposed to grab it all. You were supposed to leave like 10% in there. And you're like, well, I sat with it for 5 seconds and I grabbed it all. And so then you might have things like that you want to get rid of, like extra salt, that you ended up grabbing because you just had too much time with it. And so once again, that can lead to other types of imbalances. So the theme here is that the glomerular filtration rate basically drives the fluid to move at a particular speed. And moving at a particular speed, a particular flow rate through that nephron is what ensures that we get optimal reabsorption. And again, it's just the way that we're designed. Now, if you're sitting there trying to like envision in your head why, hopefully it will become more clear as we start talking about reabsorption. But for now, again, the theme, GFR is set at 180 liters per day, mostly to get a specific flow of fluid. When the fluid flows too fast, you end up missing some things that you want to reabsorb. When the fluid flows too slow, you end up reabsorbing too much. It's overkill. And both of those lead to problems in the blood, where, for instance, and I'll give you a true example of something that can happen when your GFR is too low. You do actually reabsorb some of the waste products, but you don't want to reabsorb all of them. But if you're just sitting there, like looking at this filtrate that's not moving, you just keep picking it out. You expect it to go by at a certain rate. And when it doesn't, you keep picking those waste products up and keep putting them right back into your bloodstream, which can be problematic and can lead to things like, gout. Now let's turn and take a look at how do we make sure that GFR is maintained at 180 liters per day. Okay, I do not want you to write any of this down. I'm only showing this to you as kind of an example of what you might predict based on what you know. We do know that glomerular filtration rate is pretty much determined by the blood pressure in the glomerulus. But blood pressure is variable. What is your blood pressure right now? You might say, it's 110/70, but on an exam day, it's 130/80. In other words, your blood pressure varies, right? It varies all the time. And you can actually use a single number called mean arterial pressure. It's not something I personally have introduced in this class, but it will be something you will need to learn about in your nursing program. It's a combination of systolic and diastolic numbers. So the only thing I want you to know here is that the higher the number, the higher the blood pressure. So if you have really high blood pressure, you would expect then your blood pressure in your capillaries to also be very high. And the glomerulus is a capillary bed, so we would expect the pressure there to also be high. Likewise, if your blood pressure was low, we would expect the glomerular pressure to be low. So if this was GFR, which again is almost solely determined by the blood pressure in the glomerulus, you kind of expect something like this, right? In other words, the greater the blood pressure in the body, the greater the blood pressure in the glomerulus, and therefore the more fluid leaks out, the more filtrate you produce. That's not what we see. Over most blood pressure ranges, GFR is kept constant. The real graph looks like this. Now again, you don't need to know what ranges these are, but this is pretty normal. In other words, it would be, if your blood pressure is way up here, then you are like, you've got other problems beyond what your kidneys are doing. And if your blood pressure is way down there, that's like, shock. So those are really bad blood pressures. But within homeostatically normal ranges of blood pressure in general, the GFR is kept constant. So how does that happen? Well, the main mechanism by which the glomerulus is able to keep the hydrostatic pressure at 55 millimeters of mercury over a wide range of body blood pressures is by changing the diameter of the afferent and the efferent arterial. So let's take a look at that. So again, where I'm going with this right now is to just look at the afferent and the efferent arterial and how their diameters impact the blood pressure. So the afferent arterial has a greater diameter than the efferent arterial. Both of them are arterioles, which means that they have smooth muscle that surrounds them. And remember, smooth muscle means that you can, I'll just draw kind of a little bit more of my smooth muscle rings here, means that you can constrict that smooth muscle and change the diameter. So if I constrict the smooth muscle around the afferent arterial, then what that's going to do is that's actually going to reduce the diameter of that afferent arterial. Well, what is that going to do? That's going to make it harder for blood to go in. So if it's harder for blood to go in, not as much blood goes in. And as long as I don't change the diameter of my efferent arterial, then what that means is that less blood coming in means less pressure against the wall. It's still the same ease to get out, and that less pressure is going to mean a lower glomerular filtration rate. What if instead I decide to relax the smooth muscle around my afferent arterial? So I'll go ahead and draw kind of a relaxed smooth muscle. Big smooth muscle rings here. then that's going to take that diameter and make it really big. That's going to allow more blood to come in. If I don't change my efferent arterial diameter, then more blood gets in. It's still difficult to get out, which means I get more a greater backlog of blood, which means the blood is going to get stuck in there and push even harder. Because again, more blood is coming in, more blood's coming in, and the existing blood can't find its way out. So it's like, I don't know, and it gets pushed up against the walls, and it's like, okay, and then squeezed out. So that's going to increase my glomerular filtration rate. So it turns out that both the afferent and the efferent arterial diameter can be changed. However, control of glomerular filtration rate is predominantly done at the afferent arterial level. Let's take a look at some examples and see if we can kind of figure out what would happen to the glomerular hydrostatic pressure and therefore the GFR in some scenarios. So I'm going to use that same kind of diagram here where I have my afferent arterial, my glomerulus, and my efferent arterial. And I'm assuming that this is kind of the default standard. The afferent arterial clearly has a wider diameter than the efferent arterial, and that this produces a pressure of 55 millimeters of mercury in the glomerulus. Now, in option 1, I am going to reduce the diameter of my afferent arterial. How can I do that? That's right. So if you constrict the smooth muscle around the afferent arterial, you will reduce the diameter. So we're going to go ahead and reduce that diameter. That's going to make it more difficult for blood to move in. So my next question is, what happens to the hydrostatic pressure in the glomerulus? It's going to go down. If the hydrostatic pressure in the glomerulus goes down, what happens to the GFR? It also goes down. Okay, in option 2 here, you can see, and I've exaggerated it here, but I've relaxed the smooth muscle and I've actually tightened the efferent arterial. Like I said, it's predominantly done by the afferent arterial, but the efferent arterial can play a helping hand. Here I've relaxed the smooth muscle around the afferent arterial and I've constricted the smooth muscle around the efferent arterial. What's going to happen? Right, so in this case, the blood is going to come in very easily, and then it's going to have a real difficult time finding an exit point. So it just starts pushing harder and harder and harder against these walls. So I expect a greater hydrostatic pressure. I apologize, put this number in here, greater than. And I expect an increased GFR as a result. Now, what I just described would show you how the GFR would change if nothing else changed, but really these are compensation mechanisms. In other words, changing the diameter of the afferent and the efferent arterial are compensation mechanisms for when the GFR is too high or GFR is too low. So let's say for a moment that my GFR is too high. I'm not going to tell you how I know that. I'm just going to say the body has sensed the GFR is too high, right? So it's too high. What do? Well, you want to bring it down. How do you bring it down? Well, if the GFR is too high, then one way to bring it down is to restrict blood flow in there. In other words, slow the flow of blood into the glomerulus. That will decrease the pressure and decrease the GFR. So how do you slow the flow of blood into the glomerulus? Right, you constrict the afferent arterial. What if instead my GFR is too low and I need to increase it? What are some things I might do? Exactly. I would try to do something like this. I would try to make it easier for blood to get in and more difficult for blood to exit by vasodilating my afferent arteriole and vasoconstricting my efferent arteriole, and therefore backing blood up, increasing the pressure in the glomerulus, and therefore bringing my GFR back up. So changing the diameter of the afferent and sometimes the efferent arteriole are compensation mechanisms that we use, or the body uses, to try to get that GFR back to 180 liters per day. So this is a negative feedback loop. Your GFR should be 180 liters per day. When the GFR starts getting too high, you're going to constrict the afferent arteriole. When the GFR starts getting too low, you're going to expand the afferent arteriole, and then that's going to give you that nice flat 180 liters per day that we saw here, even when your blood pressure ranges. Now the follow-up question is, how does the body know when to adjust the diameter of the afferent and secondarily the efferent arteriole? And it turns out that there are kind of 3 levels of control. And unfortunately, I'm really only going to get into one in this lecture. And then the other 2 are going to be saved for different lectures. But I'll list them all here, and then you'll need to kind of circle back and fill in your notes once we get to those topics. So this is kind of our last question. How is the diameter of the afferent and efferent arteriole regulated? Like, how does the body know? Expand the afferent arteriole, restrict the efferent arteriole, expand the efferent arteriole, restrict the efferent arteriole. When does it know to do that? And there are 3 regulations. 2 of them are kind of automatic, and one of them is done by the nervous system. So let me go ahead and list the 2. These are sometimes called auto-regulated, because it is a negative feedback loop that does both of these. One of them is called the myogenic stretch reflex. And that's the one that we'll look at now. And then the other one is the Juxtaglomerular Apparatus. Okay, in addition, there's an override, and that override is the sympathetic nervous system. The sympathetic nervous system override will usually kick in when the blood pressure is dangerously low. Okay, I am going to talk about this one. I'm going to kind of tease about this one a little bit, and then I'm also going to talk a little bit about that one, but it will also come back in another lecture. So again, really the only one that I can fully address right now is called the myogenic stretch reflex. Okay, so I'm coming back over here, and I am taking a look at my afferent and my efferent arteriole. And you might notice, if you can see it here, smooth muscle cells, right? And they're not really showing up here, but there they are, smooth muscle cells. When the blood pressure is very high, when the blood's coming in, that's also pushing this way, right? So what's that doing to the afferent arteriole? That's creating your afferent arteriole and having it expand, because the blood's coming in and pushing up against those walls, so it's going, whoa. Well, the smooth muscle cells sense that stretch and go, your blood pressure is way too high. And it basically constricts down. So the myogenic stretch reflex is a reflexive action by those specific muscle fiber cells, smooth muscle fibers, that are specifically wrapped around the afferent arteriole. When they sense that the blood pressure is too high, they constrict to try to reduce the flow of blood coming in. Likewise, when they sense not enough stretch, right, so their blood pressure is really low, it's barely there, it's barely pushing against the wall, they go, your GFR is going to be too low, and they're going to be like, let's open back up, and they're going to relax. So it takes a little bit of time to kind of wrap your head around the reasoning chain that I just led you through, the logic chain. Feel free to rewind and re-listen if needed. But I'll go ahead and write that summary here. All right, take a moment to write all this down. Pause the video if needed. Okay, I did not write down the converse, but you can. If the blood pressure gets too low, then the blood in the afferent arterial is not pushing against the walls hard enough. The smooth muscle around the arterial actually senses lack of stretch, and as a consequence, vasodilates. So it relaxes, and then basically what you get is whoa. And then that allows more blood to come through that afferent arterial, more blood into the glomerulus, and therefore brings that pressure right back up. So this myogenic stretch reflex actually is a very, very nice way, an easy way to really try to get that glomerular blood pressure right at 55. Even when there's a significant difference in your blood pressure gets too high, reduce the input of blood. Blood pressure gets too low, open it back up. Okay, the juxtaglomerular apparatus is another way to adjust the smooth muscle around the afferent and the efferent arterial. We know that the juxtaglomerular apparatus is in fact a juxtaposition of the afferent, the efferent arterial, and also the distal tubule as it's coming up. So I'm not going to go into any detail here, but you might have noticed that the distal tubule has a set of cells here that seem to kind of be talking to these other cells. In other words, they're located really close to each other and in great position to actually communicate. And that's exactly what happens. The filtrate composition here in the distal tubule is basically translated or transcribed over to the afferent arterial. And when the composition is off, because your GFR is too high or too low, that information is translated over, and then that allows some events to happen that we'll try to correct for that. That's going to really be discussed in another lecture. All right, our last one is the sympathetic override here. So this is really the only thing that the nervous system gets involved in. So the nervous system, the autonomic nervous system, has sympathetic neurons that are going to be synapsed to the smooth muscle around not just the afferent arterial, but some of the other renal arteries and arterioles. When blood pressure gets very low in your body, you have to go into conservation mode, where you're only going to send blood to organs that need it, like right now. And your brain is going to be one of those, your heart's going to be another one, and the kidneys, which typically receive about 20% of the cardiac output. I want to repeat that, 20% of the cardiac output, that's huge, they're not very big. So getting 20% of your blood, they can not get 20% for a little bit. So when your blood pressure is dangerously low, then what's going to happen is your sympathetic nervous system is going to switch on the override switch, and that's going to cause the smooth muscle around a variety of renal arteries and renal arterioles to constrict. And that's going to reduce the flow of blood into the kidneys. So when we think about percentage of cardiac output, under normal circumstances, the kidneys get 20% of cardiac output. With the sympathetic override, they're going to be getting a lot less. Because they're getting a lot less, then the pressure is also going to drop and your GFR is going to drop. And this is why you see a drop in GFR even when your blood pressure gets dangerously low. That's part of the sympathetic override. Okay, I'm not going to go too much into this, although if you think about it, it should make sense. So that concludes our rather long and complicated lecture that's covering the physiology of the very important process of kidney filtration. I'll see you for the next series on reabsorption.